Hey everybody. All right. So one of the reasons why we went over all of that about how telescopes work in the last talk um, is because you need the superior optics of a telescope to be able to figure out how far away stars are, which may not be readily obvious. What do telescopes and distance have to do with each other? Well, when you look at stars, either with the naked eye or even when you go and look at a telescope, right? You can't just look at a star and automatically know how far away it is, right? All the stars just look like they're up there on the celestial sphere. It's not obvious. You need to be able to see better than the naked eye can in order to figure out distance and measuring the distance to the stars and other faraway objects, stars, nebula, galaxies, all that stuff. This is a constant problem in astronomy. This is a persistent problem that we're going to be coming up against all semester long. How do we figure out the distance? Well, um, the good news is that people have figured out how to measure distances to faraway objects a long time ago. Um, by using what's called parallax. Right? The ancient Greeks figured out that uh, when you observe the same object from two different positions, that object appears that it is in two different positions. So the classic example here is if you hold your finger up in front of your nose, and go ahead and do it. Hold your finger right in front of your face. If you look at that your finger through your left eye and then your right eye, left eye, right eye, left eye, right eye, right? If you switch eyes, your finger looks like it's changing position relative to the background. Right? Your finger hasn't moved. Your point of view has moved. Your perspective has moved. That phenomenon, the phenomenon where an object appears to move across your field of view because you're moving, is what's called parallax. And the Greeks noticed this, and the Greeks figured out, because around this same time that, in the golden age of Athens and the golden age of ancient Greece, people were doing all kinds of stuff for the first time: astronomy, geometry, trigonometry, um, as well as all the philosophy and playwriting and all the other things that ancient Greece is famous for. And they realized that with this observation and with this newfangled geometry that they were inventing, you could actually figure out the distance to an object without actually having to travel there. Whether it's a mountain that's really far away, you can figure out the distance to that mountain without actually having to travel there by using trigonometry, by using triangles. This is the same time in ancient Greece. This is the time where you had people like Pythagoras, right? Experimenting with right triangles and saying, well, you can do this for any triangle, right? Here on Earth, people use this for surveying. But in astronomy, you can do this by saying, all right, if you've got a right triangle between the Earth, the Sun, and some star, then look what happens, right? If the Earth is moving around the Sun, then when the Earth is, let's say we start here, right? If the Earth is right here at a certain day of the year, then this nearby star is going to look like it lines up in front of this star. And as the Earth moves around the Sun over the course of 6 months later, the Earth is here. And then from the Earth's point of view, which is where we are, this nearby star is going to look like it lines up with this star. So that over the course of 6 months, the star starts over here and the star wobbles over to the left over 6 months. And then over the next 6 months, that star is going to appear to shift back over to the right, and it'll come back where it started out 1 year before. And so there were a group of astronomers. They probably didn't call themselves that, because I think the term astronomer was more of a recent invention than 2,000 years ago. But they were arguing that said, if the Earth goes around the sun, then we should be able to see. If the Earth is traveling through space around the sun, then stars should shift over to one side over 6 months and then shift back over the next 6 months. Now, notice what I keep saying there. If the Earth orbits around the sun, well, that probably doesn't ring right to your ears, because in ancient Greece, people thought that the sun went around the Earth, not the other way around, right? People back then thought that the Earth was the center of the universe and that the sun went around the Earth. And the thing that's been largely forgotten from, common knowledge is that there actually was another group of astronomers at the same time that said, no. If there's some object at the center of the universe, doesn't that big bright sun in the sky make the more obvious choice? Right? If there's one thing that's sitting still that everything revolves around, I think it's the sun. So there was this debate in ancient Greece about what goes around what. Does the sun go around the Earth, or does the Earth go around the sun? And a group of these, we'll call them astronomers, they said, well, we've got an experiment, right? If the Earth goes around the sun, then the Earth is moving through space. And if the Earth is moving through space, then stars will exhibit parallax, right? We on Earth will see these nearby stars shift over to one side over 6 months and shift back over to the other side over the next 6 months. This is an experiment we can run to determine, does the Earth go around the sun, or does the sun go around the Earth? Now, what's your experience? Do you see some stars shift relative to each other? Do you see stars change alignments? Do you see stars shift relative to the background stars over a few months and then shift back over the next few months? Do you see the constellations and the asterisms change shape? Do you see the stars move relative to each other over the course of the year? No. Right? The asterisms all stay the same shape. The Big Dipper always looks like the Big Dipper. Orion's belt always looks like Orion's belt. The stars don't move relative to each other over the course of the year. At least not to the naked eye. And this is what the Greeks got wrong, or this is what the Greeks didn't know, because the ancient Greeks, telescopes hadn't been invented yet. Telescopes wouldn't be invented for another many centuries. If all you have is the naked eye, then yeah, the stars look like they're standing still. And so the Greeks did the logical thing. They said, well, if we don't see the stars shifting with parallax, then the Earth must not be moving. And if the Earth isn't moving, then the Earth must be sitting still at the center of the universe, and the sun must be going around the Earth. We've solved the problem. All right, mystery solved. Now we know the Earth is sitting at the center of the universe. And that's what people thought for the next 1,500 years, almost 2,000 years. Right? We make fun of the fact that, back then they thought the Earth was the center of the universe. Well, that's what the evidence told them. Right? The evidence, they ran the experiment. They weren't just making things up. I mean, most of them, some of them weren't making things up, right? They weren't just making up that the Earth was the center of the universe. They said, well, what does the evidence suggest, right? The evidence says stars don't have parallax, and therefore the Earth must not be moving. So if the Earth isn't moving, the sun must be moving around us. Problem solved. Right? Now, 1,500 years later, they realized, oh, actually the Earth is going around the sun. So the stars must have parallax, right? During the Renaissance, when they realized that the Earth does go around the sun, then people came back and said, oh, stars must have parallax. The problem is the parallax of stars. This diagram here is exaggerated, clearly. Like if stars shifted this much and then shifted back this much over the course of the year, you'd notice. The fact of the matter is, because the Earth is orbiting around the sun, stars do have parallax. It's just very, very imperceptibly small to the naked eye. Remember when we were talking about telescopes and we talked about the resolution limit, right? The angular resolution of a telescope is the size of the smallest detail that you can see. Well, because our eyes are not very big, you can't see, with the naked eye, you can't see the tiny little parallax shifts that stars do. But with a telescope, you can see that, right? The first telescope that was made big enough to actually see the parallax of stars wasn't until 1838. Friedrich Bessel. Friedrich Bessel is sort of a big name in optics. He was making the best lenses in the world back then. And so he built the world's biggest telescope at the time, which wasn't very big. It was just a few inches across. But it was big enough that you could actually see these tiny little parallax angles. How small are these parallax angles? Well, basically, if I were holding a dime, and if I were standing a kilometer away from you, that's how tiny these parallax angles are, right? Imagine somebody holding a dime up in the air for you to see, but they were standing a kilometer away from you. How big is a kilometer? A little more than half a mile, right? That's how tiny. Would you be able to see with just your eye? Would you be able to see someone holding a dime if they were standing half a mile away from you? No, it would be unresolvably small. Your eye wouldn't be able to pick it out. But if you had a pair of binoculars or a telescope, you could see the dime just fine, right? For the exact same reason that we talked about last time with telescopes, these parallax angles, these little shifts back and forth that stars do over the course of the year, not because the star is moving, but because the Earth is moving, these angles are so small we don't measure them in degrees. We don't even measure them in arc minutes. Parallax angles are measured in arcseconds. Remember, what is an arcsecond? An arcsecond is 1/60th of 1/60th of a degree. Right? Tiny, tiny angles. Why? Right? Why are the parallax angles of stars so tiny? Well, let's do this experiment again here. Right? Put your finger in front of your nose and look at your finger with just your left eye and then just your right eye. And your left eye and your right eye. And you notice that your finger looks like it's shifting back and forth. Now hold your arm out. Hold your finger out at arm's length. All right? If you hold your finger farther away from you, now look at it with either eye. Look at it with your left eye, your right eye. Your left eye, your right eye. Your left eye, your right eye. All right? So if you hold your finger farther from your face, your finger still has parallax. Your finger still looks like it moves back and forth, right? But less, right? The farther away your finger is from your face, the smaller that parallax shift appears to be. So this is why the parallax angles of stars are so tiny, because the stars are really, really far away, right? The stars are, this is the one thing the Greeks got wrong, right? Other than that, the reasoning that the ancient Greeks did was pretty sound, right? The thing that the Greeks got wrong was that they thought the stars were just up there in the sky a few thousand miles away. Right? They couldn't conceive of the fact that stars would be trillions of miles away. And so they thought that, yeah, if stars are only a few thousand miles away, you would be able to see their parallax with the naked eye. But since stars are much, much, much farther away than they thought, that means that the parallax angle of the stars are much, much, much smaller. So small that to the naked eye, they don't look like they're moving at all. But this, using some trigonometry, using the small angle approximation that you played around with in the homework, you can take those trigonometry equations, which, if you can avoid, if you can avoid actually doing the trig in long form, why not, right? So the trig equations simplify such that all you've got to do is take that parallax angle, take the parallax angle of that star. If you imagine a right triangle here, right? Because trigonometry is all about right triangles, right? If you remember trigonometry, if you know the length of one side, and if you know one angle, you can figure out everything else about that triangle. So we know what the length of this side of the triangle is, right? What's the distance from the Earth to the Sun? It's 1 AU. And so if we measure this parallax angle, if we have that angle, we can figure out this side of the triangle, which is to say, we can figure out the distance from the sun out to that star, or from our solar system out to that star. And that equation, that relationship between the distance to that star and the parallax angle is simply this, that the distance equals 1 over the parallax angle. The other reason why this equation is so simple is because we've picked our units conveniently. We're going to make up a new unit of distance. We're going to call it the parsec. I know I mentioned this a couple of lectures ago about parsecs, but this is where I'm going to explain to you what it is. Right? 1 parsec is defined as the distance to a star if that star has a parallax of 1 arcsecond. So you always, in this equation, you always measure the parallax in arcseconds. And as long as the parallax is measured in arcseconds, the distance pops out in units of parsecs. Because, the reason why this works is because we've defined a parsec as being based on parallax in arcseconds. We're making up a new unit of distance. We're not going to measure the distances to these stars in AU. We're not going to measure it in light years because it would be easier if we just made up a parsec and said, well, if a star has a parallax of 1 arcsecond, 1 divided by 1 is 1, that star has a distance of 1 parsec. If you want the distance to that star in light years, well, measure the distance in parsecs and then convert it into light years. That's it, easier. But this equation works because P is always in arcseconds and D is always in parsecs. Right? And so the first star that Friedrich Bessel was able to measure the distance to was this star named 61 Cygni. And he measured that the parallax shift, that little parallax shift in that star is 0.3 arcseconds. And so you say, well, 1 divided by P, 1 divided by 0.3 arcseconds is 3.3. So therefore 61 Cygni is 3 parsecs away. Boom! Now you know how far away that star is. Right? you can't measure the distance to the star directly. You're not looking at the star and going, well, obviously that star is 3.3 parsecs away. No, you're watching the star wobble back and forth. You're watching that star shift with parallax over the course of the year, and if you measure how much the shift is, or if you measure how much that it shifts by, then you're able to calculate the distance out to that star. Right? Now that we've defined the parsec, we say, well, what is a parsec? What is a parsec in terms of these other units that we know? Well, 1 parsec is 206,265 astronomical units, or about 3.26 light years. This is going to be the last of the major units of distance that we're going to use in this class. So, again, pick the right tool for the right job. Right? If you want to measure the distance in AU, all right, go for it. If you want to measure it in light years, go for it. Whatever's easier. Use whatever's easier. For most of the time in this class, and for most of the time in astronomy, we measure distance in parsecs. Why? Because it's easier. Because if you measure the parallax angle, out pops. If you measure the parallax angle in arcseconds, then the distance in parsecs pops right out of this equation, and so we'll just leave it in parsecs. If you absolutely needed it in light years, or AU, then you can convert from parsecs into light years or AU from there. But if parsecs will do the job, then just leave it in parsecs. If you start talking about far away stars that are thousands of parsecs away, then you would just, instead of inventing a new unit of distance, we'll just start using metric prefixes. So if you've got a star that's 10,000 parsecs away, all right, you could say, well, that star is 10,000 parsecs away, or you could just shorten that to 10 kiloparsecs, where kilo means 1,000, right? Or if you've got a galaxy that is 5 million parsecs away, you could say, oh, that star is 5 million parsecs away, which gets to be kind of cumbersome if you have to write it over and over. So you could just say, oh, that star is 5 megaparsecs, right? Where mega means million. So 5 million parsecs, 5 megaparsecs, same thing. The reason why I said that measuring the distances to things is a constant problem is because this doesn't work for everything. This parallax method to measure the distance eventually fails. Right? Why? Because as stars get farther and farther and farther away, the parallax angle gets smaller and smaller and smaller. Right? Just like your finger in front of your face. The farther you hold your finger in front of your face, the farther you hold your finger from your face, the smaller that parallax shift becomes. And so at some point, eventually, a star will become so far away that its parallax angle is smaller than the resolution limit of your telescope. And if that star's parallax is too small to see, then the star will just look like it's standing still. Right? You can still see the star, right? There's the star, it's giving off light, I can see it. But if the star is so far away, the star will just look like it's standing still. Now, in the last few years, we have really been reaping the benefits of the Gaia spacecraft and the Gaia mission. Because there have been, ever since Bessel proved that it can work, people have been trying to measure the parallax angles and calculate the distances to lots and lots and lots of stars. Up until a few years ago, the best data set with distances was done by a spacecraft in the early 90s called Hipparcos. And Hipparcos was able to measure the distances to stars. It was able to measure the parallax and calculate the distance out to a few hundred parsecs, which is amazing because there's millions of stars within 500 parsecs. And so we had the distances for millions of stars. That's awesome. But the problem is our whole galaxy is tens of thousands of parsecs across. So if the whole galaxy is 30,000 parsecs across, 500 parsecs is just our own little local neighborhood. A few years ago, they launched the Gaia mission, and Gaia's main job was to orbit the Earth, map the sky, and measure the parallax shift of stars over and over and over again for several years, and measure those parallax shifts really, really carefully. The Gaia mission has been such a staggering success that it is able to measure parallaxes down to as small as 1/10,000th of an arcsecond. Now, how far away is a star if it has a parallax angle of 1/10,000th of an arcsecond? Right? If a star has a parallax as small as 1/10,000th of an arcsecond, 1 divided by 1/10,000th is 10,000 parsecs. So that the Gaia spacecraft has measured the distances and the parallaxes of stars out to 10,000 parsecs. There are over 1 billion stars in the Gaia database. So we now know with really fantastic precision. I feel like I'm not acting here. I'm like, my enthusiasm is genuine. It is an awesome data set where if you want to know, 10,000 parsecs is a third of the distance across the galaxy, right? We've got the distances and the parallaxes of literally over 1 billion stars. And all you got to do is go on the Gaia website and look it up. It's fantastic. It's an amazing tool. But it's not all the stars. Because the galaxy is a lot bigger than 10,000 parsecs. So most of the stars in the galaxy are actually outside of that radius. Right? Even with the best data we have, even with Gaia, eventually the stars get beyond 10,000 parsecs, and the stars that are farther than that, we can still see them, but their parallaxes are so small that their parallax shifts are below the resolution cutoff of the telescope, and therefore those stars just look like they're standing still. They don't have a parallax that we can observe. And if we can't see the parallax, then we can't measure the distance to that star using parallax. So what do? If we can't measure the distance to that star using parallax, we got to invent some other tool to do it. And that's why I say this is one of the recurring themes we're going to be hitting on all semester long is, well, how do we measure the distance to those objects? Because if a star is close enough that you can measure the parallax, you're good as gold, right? You've got the distance right there. Plug the parallax into the equation. Boom, there's the distance. If a star is too far to get the parallax, then we got to come up with something else. We got to come up with some other way of measuring distance. What method is that? That's another story for another day. We'll get there. All right? But at least for stars that are close enough that they're in the Gaia database, boom. You got the distance. There we go. Now we can look at that star and say, well, that star, what's its parallax angle? Okay, calculate the parallax angle. There's the distance. For example, let's do a bit of practice here. Right? If you've got a star like Alpheratz, and if that star has a parallax angle of 0.1 arcseconds, what's the distance to that star? Well, the distance is 1 divided by the parallax. So 1 divided by 0.1 arcseconds. 1 divided by 0.1 is 10. So the distance to that star must be 10 parsecs. Right? Using parallax, the distance always comes out in parsecs. So D it is. If you discover a previously unknown star, you've discovered a brand new star nobody even knew about, and you discover that that star has you measure that that star has a parallax of 4.5 arcseconds. What's the distance? What is the distance to that star? That star is going to have a distance of 0.2 parsecs. So, all right, so D it is. What do you think? If there's a star that you just discovered, a star that nobody knew existed before, and that star has a parallax of 4.5 arcseconds, what can we figure out? What can we say about that star? What do you think? How far away is this star? This star with a parallax of 4.5 arcseconds, it is 0.2 parsecs away. Is that a lot or is that a little? Remember when we were talking about scales, right? Is 0.2 parsecs really far away for a star, or is it really close for a star? Well, what did we say? The nearest stars to our solar system are how far away? They're a few light years, right? How many light years? Details, right? But nearby stars are a few light years away. And seeing as 1 parsec is only about 3 light years, that means how far away are nearby stars? Nearby stars are a few parsecs away. So all of these nearby stars in our galaxy, all the nearest stars to us are a few parsecs away. And then you just discovered a star that's only 0.2 parsecs away. So you've discovered a star that nobody knew existed, and you've discovered that it's really, really close to us. It's only 0.2 of a parsec away. How can that be? How can a star have gone undiscovered this whole time when it's right in our own backyard? It's right next to us. It's only 0.2 parsecs away. It must be really faint. Right? This star must be really, really dim that nobody discovered it yet, even though it's super close to us in the galaxy. So there's a relation. Oh, so the answer must be B. There's a relationship between brightness and distance, right? If a star is farther away, what's it going to look like? It's going to look dimmer. If a star is closer to us, it's going to look brighter. So if we want to figure out things about stars, if we want to figure out things like brightness, luminosity, if we want to know why does a star look the way it does, we got to figure out the distance first, right? If you see a star, Sirius, let's say, right? Sirius is the brightest star in the night sky. Is Sirius the brightest star in the night sky because it's really, really close to us? Or is it the brightest star because it's giving off more light than any other star? Well, if you don't know the distance, then you can't answer that question. We need to be able to figure out distance by using parallax or by using some other method in order to answer the question about why are stars as bright as we see them. What's really going on with stars, right? Not just what stars look like, but what's really going on? How much light are they actually giving off? How hot are stars? What's going on? How do stars work? All of those questions start to become answerable if you've got the distance. So that's why this is such an important problem. And it's one that if you have the parallax, you can solve. And then, if you know how far away a star is, now you really know something real about that star. You know its distance from us. And then you could start answering all those other questions about what's the star like really. All right. So with that, um, oh, with that, I'll give you a little bit more work. Go ahead and open up the lecture tutorial book, the green book, to page 41 and work on that tutorial from pages 41 to 43. Should take you about 10 or 15 minutes. And then go ahead and turn that into me. And then go ahead and work on the very first tool belt item in the Astronomers tool belt, the lab book. All right, all of this will be on the list in the modules for you to see. But we're at the first tool for figuring out things about the universe, right? Measuring parallax and distance is our first tool in our tool belt, so that's where we're going to pick things up in the green book and then in the lab book. All right, so go ahead and get that done. If you got questions, ask them, and have a good day. All right.